Clean water, something that we take for granted. But it hasn't always been that way, and it still isn't in much of the world. Since prehistory, we've regarded energy as a commodity. It takes effort to go out and find firewood and dry it, or to dig fossil fuels from under the ground and process them. But water is something different. It's something fundamental. It falls from the sky, and it runs in rivers and streams. It's something that we regard pretty much as free. But as we make the transition towards a renewable energy economy, the distinction between energy and water is getting a little bit less defined. Sunlight and wind, like water, are free, but it takes machines to harvest them, process them, store and distribute them. Half a degree of global warming ago, I gave a lecture at the Royal Institution in London, and I talked about droughts and flooding events around the world in the future tense. Now that seems very dated today. When we talk about climate change, we think of it as an energy problem, which of course it is, but it's also a water problem. It's a water problem because all the solutions to climate change depend on water, and it's a water problem because water is our most precious resource, and the tenure of humankind on Earth depends on access to water and not too much of it. To an engineer, energy and water go hand in hand. Hydro generates more electricity than any other renewable energy form by a factor of 2. It's also dispatchable. You can turn it on when you want it and off when you don't. You can store electricity with pumped hydro by pumping water up a hill when it's cheap and abundant and letting it back down to turn a turbine when it's expensive and in short supply. In fact, 95% of electricity storage is in the form of pumped hydro, and it's growing faster than all other forms of electricity storage put together, much faster than batteries. Solar photovoltaics is the fastest growing form of renewable energy. It's growing exponentially at the moment, and that's a real exponential, not just what the media call an exponential. But it takes 600,000 litres of water to make just 1 kilowatt of PV cells, not to mention the water that's needed in their lifetime to keep them clean, often in desert areas. So energy is fundamentally dependent on water. But water is also fundamentally dependent on energy. If you look at pretty much any photo of an open waste dump in the global south, you'll see a lot of plastic water containers. In fact, across the human population, we throw away about 60 of them on average every year per person. That accounts for 200 million tons of carbon dioxide emissions. 600 million people in the world still boil their water to drink, one of the primary drivers of deforestation in semi-arid areas. In fact, 10% of global greenhouse gas emissions can be traced to the harvesting, the use, the storage and distribution and the treatment of water. That's massive. That's significantly more than shipping and aviation put together. Irrigation sits at the heart of the energy, food, water nexus. It accounts for approximately 70% of human freshwater use, and it's a massive energy consumer as well. In irrigated agriculture, pumping often uses as much energy as fertilizer, the biggest single agricultural energy input. Only 20% of the world's cultivated land is irrigated, but that 20% accounts for 40% of our food production, from which you can work out that irrigated land is on average almost 3 times as productive as non-irrigated land. Now that doesn't mean that all you have to do is go and spread loads of water on the fields around Warwick and they'll grow 3 times as much food. No. It's true because most of our food is grown in the tropics, where there's more light and plants grow a lot faster, but you have to add water to achieve that. Now, this isn't actually a map of food production, it's a map of water stress. These are the areas in the world where we're pumping water out onto the land, the red areas, faster than it can be replenished. And that's a problem, because these are the breadbaskets of the world, and we're losing them at a rate of about 23 hectares a minute. Now, contrary to popular opinion, most of sub-Saharan Africa doesn't actually have extreme water stress. Even the drought-prone areas of northern Kenya, South Sudan, and Tanzania, the big issue is much more water management and a lack of infrastructure. If I overlay a map of electricity grids around the world, you can see that these are also the areas that don't have grid electricity. Most farms in these areas are small holdings. This is a small holding in Western Kenya during the dry season. There's little to do because nothing will grow. And even in the wet season, yields are low and vulnerable to droughts and flooding. And this is a massive problem. But it's also a big opportunity. The rapid reduction in the price of photovoltaics, coupled with mobile money, is driving an explosion in the uptake of small solar surface pumps such as these. They're cheap, efficient, reliable, easy to access to repair, and when they do go wrong, you can get them repaired locally with ease. You can move them around from application to application on the farm, and in fact, when they're employed, a farmer's income can typically increase from 4 to 6 times in a single year. Not bad for ROI. But there's a problem. You have to have access to water within about 7 meters of surface level, because a surface pump can't suck more than about that. You'd need more than a vacuum, and that's not possible. Unfortunately, less than 10% of the population of sub-Saharan Africa have water within 7 meters, so they have to dig a deeper hole or drill a borehole and install a submersible pump below the waterline, often in silty, mucky conditions, to pump water, literally push it upwards from below. This requires a lot more power because there's more work to do. They're also a little bit less efficient to fit within the space available, which means thicker and longer electrical cables. They typically have some kind of safety cable or rope in case the pipe breaks. And the problem is that they break. And when they break, they're hard to access to fix. They break for all sorts of reasons. They run dry, they seize up, they clog up. And you certainly can't move them around from application to application on the farm. But what if we could extend the benefits of surface pumps to deep water? What if we could come up with some sort of cheap device at the bottom of the well that had no fault-prone parts in that location? Then we could access a much bigger proportion of the population. Now, our story begins in 1792 in southeastern France. These are the Montgolfier brothers. They are famous for having invented hot air balloons, but they also invented a pump called a hydraulic ram pump or a hydram. This is a pump that sits in a stream and uses the hydropower of the stream to push some water up to a much higher level. And they're incredibly simple things. They have only 2 moving parts, and they rarely go wrong. And if those moving parts are worn, they'll often continue to run. There are, in fact, examples of hydrams that have run continuously for over 100 years. You still see them from time to time. Here's one I videoed on a cycling trip recently. But despite their mechanical simplicity, the physics behind them is quite involved. It was first described by Russian aeronautical pioneer Nikolai Zhukovsky in the 1890s, and in much greater detail right here in Warwick in the Development Technology Unit in the 1990s. But the problem is they're incredibly niche. You have to have access to water to gain access to water. But what if we could take this compelling, ancient, efficient, and simple technology and put it to a much bigger application, that of lifting water from deep below ground? And that is exactly what we did. So we reimagined a hydraulic ram pump, and we pump water down to it with a surface pump instead of it sitting in a stream. That water is returned, carrying about the same amount again to the surface level. We built prototypes, originally from drainage fittings. We didn't quite manage to get down to 2 moving parts, but we settled for 3. In the middle here is one which is little more than a ball that goes backwards and forwards between 2 pipes. The other 2 little more than flaps over holes. We tested it in stairwells, hanging off scaffolds, off the sides of buildings. We drilled several boreholes, this one in my back garden. We built wide ones, narrow ones, long ones, short ones, whatever we could think of to try and make the thing break, we would do, and learn from our failures and iterate the design. We tested it in back gardens, on farms. There's even one hanging off a cliff in the Alps. After 3 years of work, we were ready to put one onto a real working small holding. I will never forget the moment that the first water came out of the ground, and the farmer, Johnson here, with tears in his eyes, told us about his childhood spent lifting water with buckets day in, day out, finally to become a thing of the past. And then we went global. Kenya, India, Bangladesh, Zambia, Ghana. All the time changing the design to make it more user-friendly while starting to think about how we'd actually manufacture this thing. We iterated it again to take account of local plumbing practices and to make it possible to repair it in the field with just 1 or 2 tools. And then in 2020, we decided we were ready for production, which we set up in Shanghai and in Birmingham. And here it is, After 5 years of work and 5 million of investment, the FlexExtend, the world's first deep well hydraulic ram pump. Whilst we were setting up our production lines, we went back to Kenya to visit our earliest installations. They were all still running like the day that they were installed, which was great, but we were in for a surprise. In priority to using water for irrigation, people were using it for domestic tasks, drinking, cooking, and of course, washing. Not just for the farmer and their own family, but for all the surrounding families. In fact, in one case, 40 households and nearly 200 people. And that brings us to the other aspect of water, the smallest by volume, but where water quality matters the most. Sadly, scenes like this are still far too common. In fact, 2 billion people, a quarter of the world's population, still lack access to safe water. Diarrhea is the second leading cause of death in children under 5. What do we do about this? We've talked about how we access water, but how do we make it safe to drink? Well, often the simplest thing to do is not to pollute it in the first place. And the established way to do that is to cap wells to prevent surface water running into them, the primary cause of pollution, and to install pumps to prevent hands and ropes and buckets contaminating the water, the second leading cause of pollution. And actually, that gets you 80 to 90% of the way there. Many of these sites have water that is drinkable at source. Since about 1980, 1 million of these have been installed in sub-Saharan Africa alone, and the proportion of the world's population with access to safe or improved water has increased from about 45% to nearly 90% today. Meanwhile, mortality from diarrhea in under 5s has come down by a factor of 5, whilst the world population has almost doubled. But there are problems with hand pumps. Between a quarter and a third of them are broken, and they can only serve one person at a time. You often see long queues such as this. In fact, round-trip journey times to collect water are typically over 30 minutes, twice a day. 80% of water collection is carried out by women and girls. And we now know that there's almost a one-for-one anti-correlation between water collection times and school attendance rates. So we thought, putting 2 and 2 together, that if we could transform the economics of irrigation and the reliability, perhaps we could do the same for community water supply. So we went into partnership with an organization called Fundifix in Kenya, an excellent organization that not only install water points, they also provide an important ongoing maintenance service. We set up 2 pilot sites together, each serving 3 taps in Kitui, north of Nairobi, and the results were remarkable. Water was available at the taps 99.6% of the time, compared to a baseline average of less than 90%. But, of course, as word got out that there were reliable water sites in the area, the queues started to grow again. So we realized that if we really want to achieve impact, we've got to do this at a much bigger scale. The few problems that we did have during the project were mainly to do with the surface pump, which we had bought in. Having solved the problems below the ground, the surface pump itself was now the weakest link. So we developed our own, and following our philosophy of size reduction and simplicity, we've managed to achieve an ideal balance of affordability, reliability, and performance. Last year, we set up 20 sites with a partner in southern Mali, serving approximately 10,000 people. And we did each site at a cost which was little over a half of the cost of a conventional solar site. Here's the first water tower going up, and here's the first tank going onto it. And I'm pleased to say that after several months, we've not had a single service event reported at any of those sites. Here's the first FlexExtend unit going into the ground, and our surface pumping equipment, importantly fitted with 2 quick release valves, so that if anything does go wrong, we can swap it out quickly for a replacement or a backup to keep the important critical water supply going. And here is the first complete water tower of 20. But most importantly of all, clean water flowing from the taps. We've now got a number of clusters of sites represented by the blue pins all over the world, and a growing number of distributors represented by the black pins. You can strap cheap piezoelectric microphones to the pipes of hydraulic ram pumps to get an output a bit like a trace from a heart rate monitor. This contains all kinds of information about flow rates, water depths, and even gives you early warnings over the mobile phone network of any potential component failures. But what about that 10 to 20% of sites that are contaminated at source? And what about post-source contamination, which we now know to be as important, if not more important, than contamination itself at source? Chlorination is by far the most common means of water treatment across the planet, but it's usually not feasible to take chlorine chemicals to remote sites. Chlorine is made by electrolysis, passing an electrical current through water that contains a salt, such as sodium chloride, as in the case of seawater, or calcium chloride in the case of hard water. And it turns out that in perhaps as many as 50% of wells, there's just enough trace chloride that we can now liberate it at source with photovoltaics alone and no chemicals at all. This device is our first direct contact chlorinator. Water comes in at the bottom, we monitor its flow and chloride levels, and we modulate electrical current to this electrolyzer here, and drinkable water comes out at the tap. We've tested this at several sites in the UK now, and I'm pleased to say that it's now on its way to Kitui in Kenya. I'll finish with these. These are the 17 Sustainable Development Goals published by the United Nations in 2015. They codify an ambition to solve the world's biggest problems by 2030. And I've outlined these two here, having rearranged them. And the reason I've done that is because these two underpin essentially all the rest. Unless we achieve safe water, sanitation, and affordable and clean energy, we won't achieve no poverty, zero hunger, good health, and quality education for girls and boys alike. And the fact is, we're behind. We need a six-fold rate of increase in the rate of progress, particularly with respect to Goal 6, to achieve this. In the UK, we cut our overseas development aid budget by 28% in 2021, and the part of that budget that went to developing new technologies to solve these problems was cut by more than 70%. And that's ironic, given that that's also the part that was creating new export industries to pay for the rest. I'll leave you with this thought. We can solve these problems. We can achieve universal access to clean water and sanitation and even energy. We have the tools at our fingertips. But in order to do so, we need to stop turning our backs on the poorest quarter of the world's population and concentrate on solving our shared challenges as a single global family. Thank you.